it's time to do some optimizations. By now you have already seen the first 3 episodes of this series, so let's jump straight into the code. First, I am doing some refactoring of the existing code, such as utilizing C++17 structured binding statements. So first, we need to add some attributes to the statements that comprise the intermediate representation of the program. Unlike what I did in the previous episodes, this time I'm opting for a simpler design and making them global static constant compile time tables. This simplifies some of my designs a great deal, for example this dump function, which can now simply do a table lookup and print that. I have spoken previously about this topic, but much in programming is work towards making the work itself easier. Programming is so much more exciting when you can type just a few carefully selected concise expressions to accomplish much. It is even more exciting when you can do concise code without sacrificing performance. This is why I program in C++ and not C or assembler, for instance. And this is the driving motive behind library interfaces like the one you see here. Now we get to the actual task at hand: optimize. To optimize the code we call this function optimize. Sounds simple, huh? Well, of course we must also define what this optimize function should do. The optimize function just calls a number of optimization methods in a sequence, looping this process until it no longer can find anything to do. The first optimization method is to delete all code that does not accomplish anything. NOP statements are an example of such code. Deleting a statement is not exactly trivial. You have to replace all references to this statement with a reference to whatever comes next after this statement. It is possible for this process to become stuck in an infinite loop, for instance if your program has an infinite while loop, where the loop body is nothing but NOPs. In any case, now that we have a mechanism that will take care of removing all NOP statements, from now on, anytime we want to delete a statement from the code, just transform that statement into a NOP, and this method will take care of deleting it safely. However, we did not actually delete anything yet. The delete NOPs function only removes the ineffective statements from the chain of statements, but the actual statement still remains allocated and pointed to in the all statements list. This is why we need a second function that does garbage collection. Any statement that can never be executed under any circumstances is garbage. It is just taking space and not accomplishing anything. The garbage collection function, GC, walks through the entire code, starting from the entry points of each function, and keeps track of which statements it was able to reach by only following the next and cont pointers successively. After no unexplored pointers remain, the function deletes all the statements that were never visited. This process is repeated until nothing more can be deleted. The next 2 optimization methods are called jump threading and deduplication. Jump threading is the concept that if there is a jump instruction and the target of that jump instruction is another jump instruction, the target of the second jump instruction can be copied into the target of the first jump instruction. In my design there are no separate jump instructions, but there are branch instructions. The same principle applies to them of course, but there are more things to match besides the jump target. Speaking of branch instructions, if we have a branch instruction that comes immediately after an instruction that sets the register to some particular value, we can deduce at compile time where the branch will go. If the value was 0, the code will progress at the next pointer, and otherwise it will progress at the cont pointer. So we can just change the literal load instruction to point to the corresponding target. While writing these optimizations, I thought of another trivial optimization which you can see here. It's not exactly jump threading, but I could not think of a better place for it. Then deduplication, which is to say the merging of identical code. If there exist 2 statements that are completely identical in every manner, including the target where they go next, All references to the first statement can be replaced with references to the second statement, and the code will still work exactly the same. This can be done by comparing all pairs of statements and finding matches, but it would be highly inefficient. To speed up the process, I created a temporary hash map. There is still the O(n)² comparison, but it is now done only to statements that were already found to have identical hashes. Now let's test what we have accomplished so far. As an example, let's have this find function which searches a string for a character and returns a boolean value indicating whether a character was found. Now let's run the compiler. On the left there is the unoptimized parse tree, and next is the optimized parse tree. The optimized parse tree is slightly longer, but that's alright. Next is the statement-based representation of the function. And then the same after optimization. You can immediately see the optimized code is so much shorter. How did that happen? Let's find examples of the individual transformations. Over here you can see a NOP statement was deleted. The original code had a few NOPs here and there, but the optimized code has none. Then there are quite a smaller number of branches in the optimized code. And over here you can see an example where a register is set 1, and after that immediately a branch follows. And in the optimized code no such branch exists because the branch was inlined. The same also happened here. The register was set to 0 and the branch was inlined, so this statement is immediately followed by this statement in here because of the optimization. So what we did so far seems to work alright. And that's pretty much everything we can do by just looking at individual statements or pairs of statements. To do better, we must track the lifetime of each variable. Variables are the same as registers in my compiler, just so you know. The lifetime of a variable begins from one or more writes, and it may include a number of reads. Besides that, there can be a number of statements that do not interact with a variable in any manner, but which could read it if they wanted. This comprehensive map of access information for all variables is built in much the same manner as the garbage collector, tracing through the whole program, but it is a bit more complex. As we trace the program, we must keep track of every possible register that is accessed in the program and identify where this register was written to. This information is saved and possibly updated multiple times until all data has been collected. There are 3 possible types of sources for each variable. It may be unknown, for example if the variable is erroneously read before it's ever written to. It may come from a function parameter, or it may come from a statement that writes into it. These 3 options are identified in the variant source type. Commence music. In some situations, it may make sense to keep track of variables even if they are copied from a register to another register, so I also added an option that makes it possible to do that. Additionally, there are some situations in which we utilize the knowledge of whether a branch was taken as a signal that the register that the if-and-then statement tested had a particular value. Now, how do we utilize the access information? The possibilities are endless. To begin with, remember the code that deletes instructions that do not accomplish anything? The routine that deletes knobs and that sort of things. Well, by utilizing the access information, we can now add to the list of deleted statements those statements which write to a register that is never read thereafter. This is called dead store elimination. Writing something that is never read by anyone is called a dead store. We eliminate dead stores by deleting statements that write into a register that will never be read before it gets overwritten. But this was just the start of it. There is so much more we can do. In fact, most of what we did in episode 2 in the constant folding function, we can also do to this representation of the code. It was easier in episode 2 than it is now, but it is more rewarding here than it was back then. The idea is the same. If the parameters to an operator, such as negate or an add, have constant values, the mathematical operation can be deleted and replaced with a statement that just loads the result. But the tricky part is this. The statements do not have number parameters, they only have register parameters. To figure out which values there are in those registers and whether the values are constant to begin with, we need to do some analysis. This function getLiteral will return a constant value or it will return nothing. In C++17 you can convey this kind of situation with std-optional. Std-optional long means that either this variable contains a long integer value or it contains nothing. When it contains nothing, it does not mean that it has some implausible value, nor that it contains a null pointer. It literally means that it does not contain an integer value at all. Behind the scenes it might be implemented as a pair of long integer and a boolean flag, but we do not need to care about that. It's perfect for our purposes. We check all possible sources for the value in this register at this moment and see what those sources are. The source can be a function parameter or it can be a statement. If it's an init statement with a number literal, we take that. If the return value has already been set and this value differs from the return value, we return nothing. In other words, either all sources agree on a single integer value or we have nothing. Oh, by the way, if-and-then statements can also be sources of integer values, even though they write into nothing. If one can reach the target statement from the if-and-then's no branch, but not from its yes branch, the value was definitely 0, and vice versa. So how to figure out whether some statement can be reached from some other statement? Basically the same way we did garbage collection earlier. It's almost the same, except now the process only begins from the source statement and not from all function entries. The function does not need to be perfect. We are not solving the halting problem here. If it gives false positives, it does not matter. What matters is it must not give false negatives, so it must discover all possible paths from point A to point B. Paths that hit point A a second time before hitting point B are exempt, so we don't need to worry about e.g. loops or recursion. There are situations where it is useful that if-and-then statements are treated as value sources, and situations where it is actually harmful, so we run this process twice, first without if-and-then statements and then with if-and-then statements. So let's continue. Besides neg and add, we can deal with literal values in the x statement, or the if-and-then statement. If we know the source register contains a constant value, we can replace the if-and-then with a knob and just hardcode the target. The init statement is used for initializing a register with a number constant or with a reference to a global variable or function or both. If at the point of the init statement there exists some other register that already contains the same value, we can replace the init statement with a copy. To do that, we work through all registers that are alive at the point of that instruction and check if that register already contains the desired value. This optimization is a form of common sub-expression elimination, a very important optimization technique in compilers in general. It may seem like a non-optimization since it just replaces an instruction with another instruction, but we will get back to this topic later. Chances are the copy instructions can be removed altogether. Next, tail call elimination. A tail call is any situation where a function call is immediately followed by a function exit. In terms of my compiler, this would be a fcall statement followed by a read statement with the added restriction that the register number consumed by the read statement must be the same register number that the fcall produced, and the function pointer consumed by the fcall must be predictable and must point to a single known function. For identifying the source, this code uses the std optional, just like before with the literals. So a tail call opportunity was identified. In this situation, the fcall statement is replaced with a nop in order to get a single next pointer that we can later replace. After the nop statements, we may need to add some copy statements to shuffle the parameter registers into the right order, and finally the last statement is linked to the beginning of the target function. This is an illustration of how the tail call optimization works. It may look like a pessimization at first glance, but the init statement that loads the function pointer will be deleted by deadcode elimination, as will the nop statement, leaving only the copy statements. And we are about to address that right now. Now there have been several optimizations so far that produce new copy statements. There is a time and place for copy statements, but most of the time they don't actually accomplish anything meaningful. They just transfer data from a register to another. It's like printing an email. You make redundant copies. It is time to look into ways that we can elide redundant copies. This is called copy elision, and it is surprisingly tricky. The fundamental idea is this: if the register that some statement reads was created by a copy statement, change the parameter of that statement into the copy statement's source. In other words, get the value directly from the source rather than using its copy. A noble idea. Unfortunately, there are myriad ways that this can go wrong. Not only must the source to the copy statement be still accessible at the moment the second statement is executed, there must be no other statements that can be sources of the target register at the point of the second statement, except other copy statements, which are fine as long as they all have the same sources which are still accessible at the point of the second statement. But there is also another way at optimizing copy statements, and that is from the point of the source statement. If the register that some statement generates is only read by a copy statement, the statement could write directly into the register that the copy statement writes to. And this method has even more caveats than the previous method had. I am at a loss to even describe the process of taking care of all these conditions in an insightful way, so I will just let the code roll. And it's finished. Time to check the results. Remember the find function from earlier? This is what it becomes as a result of the new optimizations. It's pretty short now. There are no copy statements anywhere in it. Even the recursion was converted into a tail call. Here is another example. You can see the optimized code is dramatically shorter. Optimization is art. As long as the optimized and unoptimized code accomplish the exact same output for the same input, there is no right and wrong. However, as a general principle, there are two distinct categories of optimization: optimizing for size and optimizing for speed. Often the optimizer can accomplish both, but for some optimizations one needs to choose between smaller code that is slower and faster code that is larger. There are still a few tricks I want to do before we get to the final step of the compiler, code generation for the target machine, so stay tuned, more is coming. Gora mahogot slaan.